expecting to see Eric Budish. He'll be sorely disappointed. He's a University of Chicago economist who was supposed to talk today, but got stuck in an avalanche. Somewhere in Colorado. I mean, he's actually at UC. There were no avalanches. Not a lot of avalanches in Chicago. But, so I'm Lance Fortnow. I'm a professor here in the theory group. I agreed to kind of lead the talk today. Instead of introducing myself, I thought I would mention 3 interesting facts about my student Arifin Hook. Number 1, he passed his qualifying exam today. So Number 2, if you get the latest issue of ACM Crossroads, Arifin was the guest editor on the special issue about Turing. So good for Arifin. And most importantly, number 3, Arifin is now engaged. So congratulations on all those. That excitement. So this talk, I didn't have a lot of time to prepare, so I just grabbed one of my old talks. This is a talk I gave at a lunch for the MEDS, the Managerial Economics Decision Sciences faculty in the business school. So it's kind of has a little bit of an econ bent. I mean, it's from a computer scientist, but it was given to economists. So, but that shouldn't be an issue. Okay, and this is joint work with Michele Budinich, who was a student at IMT Lucca in Italy, but he was visiting me for about a year at here at Northwestern. Should be graduating soon if he hasn't already. And this work appeared at the Electronic Commerce Conference last summer. Okay. So I'm going to talk a little bit, before I talk about the actual paper itself, let me give a little bit of background on kind of a theme of some of my research in recent years, which is taking models, macroeconomic models, and saying, well, what happened, or questions, and saying what happens when we replace agents by ones that are computationally bounded. How do we define that kind of notion, and what can we understand from it? So, this has been done quite a bit in the past. In a topic that's generally, for games, I'm going to focus on game theory today. A topic called bounded rationality. So, anyone recognize this game? Oh, they tell me the name of this game. Thank you, Nicole. I'm not training you well. So this is a typical game in game theory. It's called Prisoner's Dilemma. The way to read this chart is there's 2 players. The player 1 who chooses one of the rows, and player 2 chooses one of the columns. The story goes here is you have 2 people suspected of collaborating in a crime. You put them in separate rooms, and basically they each have to make a decision. They can either cooperate. Well, so you gotta be careful. They can either defect from. Okay, they originally decided. Okay, well, we're just both going to claim our ignorance and see what happens. They both go into these rooms, and they have the option to either cooperate with their other prisoner and then still proclaim their innocence, or defect, which says, okay, I did it, but so did the other guy. So rat out the other guy. So this is kind of a standard storyline in Law and Order, almost like TV shows. And then the idea here is if they both cooperate, they both get out scot-free. So they both get this is sort of a payoff utility. Player 1, both players get 3 points, 3 units of value, whatever that means. If player 1 cooperates and player 2 defects, let's say player 1 defects. If player 1 defects and player 2 cooperates, so what does that mean? Player 1 is now ratting out player 2. So not only does player 1 get to still go out free, but also gets a little bit of a reward. Meanwhile, player 2 is going to jail. So player 1 gets 4 points, player 2 gets 0, and then you have the opposite corner here. And then in the right-hand box is if they both rat out the other person, they both go to jail, but they both get a small reward. That's the philosophy of this game. There's only one. It's an interesting game because there's actually only one Nash equilibrium. A Nash equilibrium being one where neither player would want to change the strategy, and that's actually the right-hand corner, both affecting. Even though if they both cooperated, they would both do better. But the problem is, if one cooperates, it's in the advantage of the other one to defect. So the only true Nash equilibrium is this DB roll. And now you can play this game over and over again, for whatever reason. I mean, the story doesn't really make sense, but you could play this game repeated many times. And then what people have looked at is, well, let's look at what if these players had limited computational power. And the way it's typically done in game theory, or has been typically done, is by looking at people with limited amount of memory, or run by finite automata, which is almost equivalent to being a limited amount of memory. So you have these complex but finite automata playing this game multiple times, and then you can show results that if you have more rounds in states, or even, I think even more rounds in a logarithmic number of states, you can actually get cooperation in the long run. Because they can't remember when people defected. They're a little messy arguments, but you get these kinds of results. So it kind of explains why you get some cooperation if you play this game long enough. Now, the trouble with finite automata is it's a very simple model of computation, a bit too simple. You can't even count with finite automata. So and we have much better models of computation. In particular, the Turing machine. So this is one of my favorite pictures of a Turing machine. I'm not going to talk about what a Turing machine is. You should all know that. The advantages of a Turing machine is it really does capture computation. This is the famous Turing thesis, of which I'm a strong believer. And it also has the advantage of universal simulation. There's a single Turing machine that can simulate, and basically think of a Turing machine as like a computer program. You can write a single computer program that can take in the code of any other program and simulate it. The disadvantage of a Turing machine is sometimes it's not always the quickest way to solve a problem. It could take a very long. It could take an extremely long time, and Turing machines, being arbitrary, like an arbitrary computer program, may not halt. And even worse, you can provably show that there are some Turing machines that don't halt, but you can't show that they don't halt. You can't actually know when you simulate a computation whether or not it's ever going to halt. So that's a disadvantage of this. This is just computation, not efficient computation. You get efficient computation, we start putting restrictions on the machine. Insights by Hartmanis and Stearns in the early 60s, they started the area of computational complexity, that you can look at the running time of a computation as a function of the input size. And in particular, if you bound it by a polynomial of the length of the input, that's what we call polynomial time or efficient computation. The P in the famous P and NP question. And but there's some issues in trying to get polynomial time to work in economic models. There's no clear notion of what an input length is. I'll give you an example of that in a second. There's some sort of race condition. If you have, and that's going to come in later in the talk, where if you have two players and one is more polynomial time, a larger polynomial than the other person, it might depend on who has the larger amount of time, because one might try to simulate each other. And you can't, polynomial time. It's very hard to predict what a polynomial time algorithm will do, or backfill, or try to figure out what kinds of inputs will give what kinds of outputs. Could be very difficult. So let me give an example of the factoring game. This is a game that was invented a few years ago by Elie Ben-Sasson and father and son Kalai Ehud from the business school here, and his son Adam, who's at Microsoft Research now. And the game is very simple. We have two integers, M and R. Integers, at least say And the game works as follows. Alice sends a number, M, to Bob. Bob can see M, and then Bob has to respond with an R that is also another integer. And Bob wins. If R is a prime factor of M, then Bob gets a payoff of 2, and Alice's payoff is 1. And otherwise, Alice, if Bob fails to give this R, then Alice's payoff will be 2, and Bob's payoff will be 1. So basically, if Bob can find a non-trivial factor of M, then Bob wins this game.
Does that have to be positive?
No, the way I defined it, sorry. The way I defined it is if Alice just gives a prime, Bob can just respond the same, R equals M. Anyway, so non-Alice is...
Does it matter how many prime factors M has?
What?
Does it matter how many prime factors M has?
This is the game. Alice can throw out any M she wants.
Okay.
Bob just has to come up with some factor of M, some prime factor of M. That's basically it. It's very simple. Doesn't matter. Alice can pick whatever M she wants, any way she wants to. All right. So that's the game theoretic analysis of this factoring game. And well, Bob always wins. Every number M has a prime factor. Bob plays that one of those prime factors, and Bob always wins. Okay. So, if I were to ask, if we were to play this game, and I let you choose who you want to be, Alice or Bob, who would you want to be? You all want to be Bob, right? Good. This is a bad crowd. All right. Who wants to be Bob? I'll be Alice. Let's play. No. Now, if you're a computer scientist, and I think most of you here are, you should know that you'd want to be Alice. Why? Because if I was Alice, what I would do is pick 2 large primes, multiply them together. That'd be my M. Give it to Bob, and Bob's gonna have no chance of finding those numbers if I chose them properly. So the question they had, I mean, Ben's not like I knew this. They knew that Bob is the game theoretic, the equilibrium in this game is that Bob always wins, but in fact you'd want to be Alice. They were asking, is there a good model for this that explains this exact situation? And the challenge here is sort of the one I mentioned earlier, that there's no real notion of input size. I mean, this is a fixed game. Alice can choose whatever M she wants. So there's no notion of input size here, which makes it a particularly challenging. I mean, you can't really talk about polynomial time, which is what you want to do. So to get around it, what we did was create a notion known as discounted time. So this is an idea we stole from the economists. So basically, there's some sort of time value of money, for instance. You'd rather have $1 today than $1 a year from now, even if I adjust it for inflation. So I'd rather have the money today than next year. And so what they do is they give a discount. Money in the future is discounted. And so we do the same thing, but instead of using real time, we use computation time. So what we're going to do is discount we're going to have some discount factor, delta A, and we discount Alice's payoff by a factor of delta A to the T sub A. It should be T sub A, where T sub A is the number of computation steps used by Alice. And again, we'll also have a delta B and T sub B for Bob. And for delta, you should think of something very close to 1. 1 minus 1 over a trillion. So to think about that as kind of corresponding to today's technology. In the sense that if I do a few million computation steps, delta to 1 million is still going to be something really close to 1. Where delta to 5 trillion is going to be possibly something pretty small. Okay. And then so in a paper that I had with Rahul Santhanam, this was, I guess, the Innovations in Computer Science Conference in 2010. We showed that the following, we actually were able to characterize factoring using this discounting. So we showed that the following are essentially equivalent, that factoring can't be solved efficiently on average for any efficiently sampleable distribution, any easily sampleable distribution. So this means that factoring is hard. And basically it's saying if factoring is a hard problem to solve on average, if and only if in equilibrium, Alice gets essentially close to her full value. It's the kind of result you'd expect. If factoring is hard, then Alice should win. If factoring is easy, then Bob should win. And this shows it in the way that we get around, and the way we deal with this issue is we have a parameter gamma, and what we do is we let we give Alice a parameter gamma greater than 0, but it gets really small, and let delta of Alice be close to 1 minus gamma, and delta and B's discount to be a little bit closer to 1 minus gamma to the C for some constant C. That just captures the fact that we allow Bob to sort of run polynomially longer than Alice. We should give Bob a slight advantage in trying to factor in numbers. And then we're able to. Well, I don't want to give Bob an advantage because typically in cryptography, we want the person trying to break the code to give a little more power than the person who gets to make the code. So that's and typically that's where factoring plays in cryptography. And we at least want it to be secure in those environments. So this sort of captures this idea of factoring efficiency. So that's just an example of where we found a way to bring in, sort of a real notion of efficient computation into this game theory question. So now let me move on to the talk that I was advertising, the talk that I was working on with, the work I'm done with McKelly that was in last year's EC. Now we're going to focus on a different game, a very simple game called Matching Pennies. One of the simplest games. It's a very simple game. It's you can think of it as odds and evens, or a simplified version of rock, paper, scissors. Basically, we each hold up a coin. If the coins match, then player 1 gets 1 and player 2 gets -1. If the coins don't match, then player 1 gets -1 and player 2 gets 1. It's what's called a zero-sum game. I win, you lose. You lose, I win. It's like, whatever works for me is against you. Or essentially, what it means is the payoffs always add up to 0. And there's exactly one Nash. If you're playing this game, there's exactly one Nash equilibrium for that game. This game, there's no pure strategy. Thanks. Getting the word for a second. There's no pure strategy equilibrium, which means that an equilibrium where both players play exactly the same thing. But the strategy is just to play heads and tails uniformly, and if that happens, both players get expected output. So that's the only Nash equilibrium. Now, it's not a very interesting game to study from any computational point of view. In fact, it's a pretty boring game in general. What we want to do is look at a repeated version of this game. So now we want to play this game. Let's say we play it 10 times or 1,000,000 times or something like this. And then we take, say, the average score, the total score, after these 10 rounds. And again, the only Nash equilibrium in this game, when we play it 10 times, is for both players to independently choose their choice of playing heads or tails, independently at random, uniformly, each time along the entire way. Anything else, and you won't have a Nash equilibrium. So complete randomness is the only way to play this and achieve a Nash equilibrium. You have to play uniformly independent coins. Okay, so why am I? That seems to be pretty well settled. Why am I interested in this? And actually, computation is very simple. So why I'm interested in this is notice that this process requires 10 random bits per player. So we need 10 fully uniformly random bits of randomness. And if you're playing 1,000,000 rounds, you need 1,000,000 random bits. And true randomness is actually hard to get to. In fact, there was an article in I guess there was some interesting research that was done in the New York Times a couple weeks ago, where people were able to break like RSA, cryptographic codes, mainly because people didn't have access to truly random sources. So without the lags, so it's not, so actually getting true randomness, and it's, actually getting true randomness is not an easy thing to do, and it could be very expensive. So we decided to say, well, what happens if the players have limited randomness? And that was the idea for this talk, playing repeated matching pennies with limited randomness. First thing I'm going to do is analyze the case where both players are computationally unbounded. And then and then even that's an interesting case. And then we'll talk about the computationally bounded case, where we can do a lot better. Okay, so what happens? Okay, so let's think about. Suppose we're playing 10 rounds. Suppose you're playing 10 rounds. Suppose, okay, I'm playing you. We're playing 10 rounds of repeated matching pennies, but you only have 7 truly random bits. What would you do? Someone give me a suggested strategy. Anybody? What would you do? Would you throw out all the random bits and always play heads? No, I'm computationally powerful, so it doesn't do me any good.
So maybe I have 2 to the 7 possibilities. Out of all sequences, I choose those with equal number of heads and tails. 2 to the 7 of them, and equally likely.
That sounds awfully complicated, and it's not the best thing you can do. So it turns out the simpler thing that's what?
You have 3 remaining coins. Why don't you play 2 heads and 1 tail? And if you have 4, you can play 2 heads and 2. Half and half.
Okay.
So you divide 2 to the 10th results by 2 to the 7th. And
Wow, you're really coming up with complicated schemes.
You play
Okay.
the first 7 randomly, and then you play heads.
There you go. Nicole's got this one. Right. You just play. What, you just talk before? Yeah, let's just do something simple, okay? I've got 7 coins. Let me use up my 7 coins. And I'll just play randomly, uniformly for the first 7 rounds. And then I'm out of coins. And I'm going to assume not only I'm out of coins, I'm going to assume, for sake of argument, that the other player knows my program I'm using. So once I'm out of coins, the other guy can just predict me. So let's say I play heads, tails. I play uniformly for 7 rounds. Then I play, player 1 plays uniformly for 7 rounds, and player... then player 1 plays. I don't think I think I made a mistake in this chart. Okay, think of player 1 playing uniformly. Forget the bottom row, because I think I got that wrong. Player 1 plays 7 rounds of randomness, followed by 3 heads. Player's 2 strategy for this against this is just I'll just always play heads. If player 2 does this, then player 2 player 2 will. Oh, sorry. Player 2 wants them to be different. I really screwed this up. Say player 2 played all tails instead of all ones. If player 2 wants it to be different, then player 2 would have an expected score of would win on average about 3 rounds. Right, it would break even on the first 7 rounds because they were uniform, and it would win on the last. And then some of you, and then you're right. You could think about different kinds of strategies. You can use your randomness to decide which rounds you might want to try to improve on. You might want to, look at, play always do something which balances the number of heads and tails for some reason.
Here, if player 2 is using a pure strategy.
If once I know player 1 strategy, this is just always true. If I know player 1 strategy, then player 2 can just always use a deterministic strategy to maximize it. Player 2 could have also randomized the first 7 rounds. Would have gotten the same result. So anyway, it turns out that this simple strategy is the best one. Turns out this simple strategy is the best one for player 1. The best thing for player 1 to do is play all the randomness up front and then play deterministic. So more generally, if player 2, let's flip this around. I should have done the slide before. If player 2 plays n minus, suppose player 2 has n minus k random bits. So if player 2 plays n minus k random coin flips followed by k heads, then player 1 has a strategy which is all heads that achieves the expected payoff of k, but that's the best player 1. This is not that hard to show. The best player 1 can do against player 2 is to achieve a strategy of k, because no matter what, player 1 is going to break even on average in the first n minus k rounds. So that shows that if player 2 has n minus k bits of randomness, player 2 can use the above strategy and hold player 1 to pay off k. And it turns out that's the best player 2 can do. So as I said, that's the best. Any player 2 does anything different, well, there's different things that will still hold. Obviously, you could use the last 7 rounds, for example, instead of the first 7 rounds. But any other strategy can do no better. Okay, this is just the best thing that player 2 can do. And I wanted to give you an idea of how that's proven. First, I have to define. So suppose player 2 has some strategy. So basically, what I'm going to do is show that. Let me give you a strategy for player. Let's fix a strategy for player 2, a very generic strategy. And then what I'm going to do is show that there's some strategy for player 1 that gets an expected score of at least k. And then that shows that no matter what player 2 does, player can't do better than that strategy, which player 1 got at least k. So if player 2 plays a generic strategy, I'm going to use a very simple thing for player 1. For player 1, right. So fixed up strategy, a randomized strategy for player 2. What does player 1 do? Player 1 computes given the information he's seen so far, computes the conditional probability that player 2 will play a heads. And if that condition, then we'll call that P. And if P is at least a half, player 1's trying to match. So if player 1 believes player 2 is going to play heads with probability at least a half, player 1 will play heads, otherwise player 1 will play tails. And so that's a very simple strategy. You just do this kind of the stupid thing. You compute this initial probability, and then you just do, if at least a half, you play heads. If it's not, you play tails. To prove this result, we use potential. Actually, it's one of the few times I've ever used a potential function in a proof, because it's typically more of an algorithm thing. But here's the potential function. Potential function is that every step we let phi be the expected score for player 1 minus the log of the number of consistent random bits for player 2. Another name for this is sort of like the remaining entropy for player 2. But it might be simple to think about. There's a certain number of consistent coin toss sequences player 2 can have, and let's look at the log of that. So initially, this parameter phi is, well, at the beginning of the game, the expected winnings for player 1 is 0. And then the number of possible coin sequences, well, she has, player 2 has n minus k random bits, so the number of sequences is 2 to the n minus k. So that gives, initially phi is minus the quantity n minus k. And then we'll show in the next slide, we'll show in the next slide that phi actually increases by at least 1 every time if player 1 uses this strategy. And then that means after n rounds, the expected score, which is actually phi plus log r, the expected score is phi plus log r, right? Just resetting that potential function for player 1 is at least, phi is going to be minus n minus k, starting value, plus the n for the number of rounds, because it increases at least 1 for every round. Log r, at the end, there's still going to be at least one consistent sequence, because player 2 is playing consistently for some sequence. So it's a most 0, so that if you look at that sum, it's at least k, and that shows that player 1 gets a score of at least k at the end. So I just need to show this result that that each round phi increases by 1. Okay, and then we have to let's assume that p is at least a half. The argument is kind of just reversed if p is less than. So this means that the conditional probability that player 2 will play heads is at least a half. So player 1 plays heads. there's kind of two cases we have to break it down into. One is the case that, in fact, player 2, P equals 1, which means player 2 is guaranteed to play heads next round. In which case, R stays the same because you don't decrease the number of consistent sequences, but you're guaranteed to win. So the expected score increases by 1, so phi increases by 1. And if P is less than 1, well, then we know that 1/2 is that we know P is at least a half. We also know that P is at most 1 minus. P is at most 1 minus 2 to the. This should be minus. It shouldn't be 2 to the R. What should that be? I think it's 2 to the minus K. Turns out I don't think it's going to matter. But P is less than 1, strictly less than 1. So that's a division by 0 thing. Anyway, for this P, if you do the calculations, the expected score, the chance that I'm going to match you is going to be 2P minus 1. And you can kind of see that at the edges, right? If P is 1, this is going to be, the expected score is going to increase by 1. If P is if player 2 is playing uniformly a half, then the expected score increases by 0. And then it is linear when you work it out. So it's 2P minus 1. Now what about log R? Well, log R decreases by, well, there's a P probability that it's played heads, in which case it drops by log of 1 minus P, because it's this log factor from before. And then a 1 minus P probability that it drops by this much. So it decreases by its entropy. And then if P is at least a half, then the entropy is always at least 2 plus 2P. This is just an inequality that I'm not going to prove, but you can do the math. Just take derivatives. And this shows that phi increases by at least 2P minus 1 for the expected score, plus 2 plus 2P, which is always at least 1.
P is binary, HP is a binary entropy.
Binary entropy.
So it's measured in bits.
This is just a
Base of
potential function.
Base of
Doesn't
log
actually,
is-
just a number. I'm not actually giving units to it.
But then it's greater than. I thought it's smaller than 1. So how can it be bigger than plus 2P? It's binary entropy function. So
H of P. I don't know. H of P is. Let's see it. H of P is maximized. You're right. It's 1, right? If it's
Yeah,
1
the
half.
maximum is 1.
No, it's 2. The entropy of a truly random bit. That's 1. So wait. So did I get this wrong?
Yeah.
I know it works in the paper. So. I
It's
see.
minus 2p.
It's 2 minus 2p. It's 2 minus, and p's at least a half. It's 2 minus 2p, right? Because that cancels this. Yeah, okay, that's where I went wrong. Good catch. Right, 2 minus 2p, which is always less than 1, because p's at least a half. Okay, so like I said, we know the only possibility for true equilibrium is to play uniformly random. But let's look at an epsilon Nash equilibrium. First of all, instead of focusing on total score, let's focus on the expected score. So we expect for this. I mean, it's the same game, but just makes thought about equilibriums a little cleaner. And an epsilon Nash equilibrium means that there's no change in strategy that can increase each player's score by more than epsilon. And it turns out, as a relatively simple corollary of the previous theorem, then we can show that the end stage repeated matching pennies has an epsilon Nash equilibrium if and only if both players have at least 1 minus epsilon times n random points. So we completely characterize when there's an epsilon Nash equilibrium. And the actual strategy, just to tell you what it is player 1 plays 1 minus epsilon n random moves followed by all heads. And player 2 plays the first 1 minus epsilon n random moves, followed by alternating heads and tails. There's a technicality here about what happens if things don't divide evenly, but let's ignore that. And it's the issue that 1 minus epsilon might not times n might not be an integer. But there are ways around that. We'll just ignore that for now. This is the and it's kind of strange. You know, why would player 2 do alternating heads and tails? But trust me, this is how you actually get the equilibrium to be epsilon. So that's what I wanted. So that pretty much finishes the discussion when both players are computationally bounded. As someone had mentioned earlier, if both players are not computationally. But why do I need computational unbounded here? It's this player's one strategy. In each round, I want to compute the conditional probability P that player 2 will play heads. Even if I know player 2's strategy, that probability P is counting the number of possibilities over an exponential space. It's computing conditional probability in general is something called sharp P complete. I won't go to exact. Sharp P is like a counting version of NP. Nevertheless, let me just say, if you haven't seen it before, that being sharp P complete is much harder than even being NP complete. So it's not computationally efficient for player 1 to play this strategy in general. And that suggests that if we limit the computational complexity to players, we can get equilibrium with perhaps fewer coins. And that is, in fact, exactly what we show. And to do that, we focus on an area of computational complexity known as pseudorandomness. Pseudorandom generators. There's actually two different kinds of pseudorandom generators, and we need them both in this talk. One is sort of based on the first one, the Hofstede. There was a series. Both of these. There's a series of papers on both these results. One is mentioning the ones that give you the last theorems. So the first one is sort of based on cryptography, and it says it's by Johann Hofstede, Russell Pagliazzo in 11, and Michael Luby in 99, and they show that if there are cryptographically hard one-way functions, I'm not going to formally define it, then you have pseudorandom generators that map from a subpolynomial like n to the delta, like n to the 0.1 random bits to n bits that fool every polynomial time algorithm, no matter what the running time of the algorithm is. And then there's then there's the paper by Pagliazzo and Wigderson, same Russell and Pagliazzo, a master of pseudorandomness, and Avi Wigderson, perhaps the best known complexity theorist. And they show that under a condition about certain problems don't have small circuits, I won't get into the technicalities, then you get a pseudorandom number generator from order log n to n bits that fools all fixed n size circuits. And I can replace this n with n squared or n cubed. The difference between these, there's a different trade-off here. And this is what the point I want to make out. In here, you have a much larger seed that you need, a much larger random seed that you need, but you can fool every polynomial time algorithm. Here, the seed is much shorter, but you can only fool a fixed polynomial time algorithm. That's basically what the difference is between these two. And then, in our proofs, though I really won't use it so much in this talk, is Yao's principle, which basically says that being pseudorandom is equivalent to saying you can't predict the next bit given the previous ones, which obviously is closely related to this game of matching pennies. Okay, so I'm just going to basically state some results. Let's first take the case that both players have some n to the delta random bits for some constant delta, like think of like square root of n or n to the 1/10 or n to the 100th, something like this. And then we show the following are equivalent. One-way functions exist. There's an epsilon Nash equilibrium for epsilon down to, n is the number of, think of n as the number of rounds of the game. There is an epsilon Nash equilibrium for all epsilon equals 1, and n is also the parameter we use for in terms of polynomial time. Okay. So an epsilon Nash equilibrium for epsilon 1 over polynomial, where the players are restricted to be polynomial time computable. Again, polynomial time in a number of rounds. And it factors exactly one such equilibrium. I should rephrase should rephrase the last one a little bit. So this says there exist Nash equilibriums. There exists Nash equilibrium with much fewer random coins before with an epsilon Nash equilibrium. And it's not that there's only one equilibrium. There's only one. The equilibrium has to be very close to the expected value of 0. The strategy is very straightforward. Both players use their PRGs to generate the n bits of randomness, and then play those sequences. And then you actually have to have a two-stage proof. If both players follow the strategy, they expect the payoff as close to 0. Otherwise, one has a test that shows the other one is not pseudorandom. And stage 2 is that if one player uses a pseudorandom generator, and any other polynomial time algorithm, the payoff, it should be close to 0. If one player uses a pseudorandom generator and the other person uses any other polynomial algorithm, the payoff has to be close to 0. That's the not's there. And that's otherwise the polynomial algorithm gives a test that the PRG is not random. That's the rough idea on how you prove that.
Is C smaller than 1?
No. Think of C as a large constant. 10, 100, whatever. It affects the running time. The higher the C, the larger the running times of the algorithms you use. The other result we can get is a different scenario where we have a trade-off between the amount of randomness and the running time. So here we're going to make both assumptions of both pseudorandom generators. So not only you have cryptographic Roy functions, and also you have this circuit condition. And what we get is an asymmetric Nash equilibrium. And it's a Nash equilibrium in the sense that neither one can improve themselves by most epsilon, but player 1 is limited to be a fixed polynomial time algorithm. But, okay, so wait, how does this work? Player 1 the trade-off is here. Player 1 has a lot more random bits. Player 2 is much more limited random bits. Player 2 is a lot more random bits. Well, player 1 has to be a fixed polynomial time algorithm, and player 2 can be arbitrary polynomial time. So there's a trade-off here. The person with a lower number of random bits gets a longer running time. And you still get a Nash equilibrium, an epsilon Nash. And the proof is similar to what we had before. The actually interesting condition is what happens if both players have just order eigenrandom bits. It's still, if they're both fixed polynomial running time, you would expect, let's say both running time n to the 5th, and you have 5,000 eigenrandom bits each. You still expect there to be some sort of equilibrium, but none of the techniques from the pseudorandom generator seem to prove it. And the problem is, it's kind of a race condition. If player 1 has more time than player 2, then player 2 can't run a generator that can fool player 1 using the pseudorandom number generator techniques that we know. So let me, I think...
So what if you discount time like you did in your paper with Rahul?
if you discount time, I mean, all of our results here also hold in the kind of discounted time model, but it doesn't really change. It doesn't give you anything new either. So you could do this all with discounting.
But like somehow in the Rahul paper you solved this race condition with discounting.
If we're factoring in. But here this is based on pseudorandom generators where we don't. Based on results with pseudorandom generators we don't know. And even in the paper with Rahul, we did require that you sort of had more time for Bob than Alice. So we weren't really solving a race condition. Let's see. Once I end it, I end it. Okay. Let me just talk about my last slide. Other directions, more than say 2 actions per player, say rock paper scissors. All enough to things. I think some of the same results sort of hold, but the numbers get a lot more complicated when you actually go to 3. Now I want to mention that some of these techniques have been, I mean, the idea of using pseudorandom generators for games have been studied before. By the econ side, by papers by Gostner and Tamala, and on the complexity side by Kalayanaroman and Chris Simmons at Caltech. Though they worked on very more general models and they didn't get the type bounds that we got. Yeah, we can do a discounted. We can show similar results when we use a discount factor instead of an n. And this paper was sort of inspired, I should mention, by a result of Tai-Wei Hu. He's in meds here. Tai-Wei showed that you could take an infinite repeated game and sort of a time average model, limit of the averages, which so our stuff doesn't make sense in that model. You can actually, if you, instead of having true randomness, you can play some algorithmically random independent strings. And it'd be a good question to see how can we somehow overcome that time. Find a good answer for that. That's something else that we're looking at. Okay, thanks.